Hello everybody, welcome back to this training on natural language processing. In this video we will discuss about a very important concept of natural language processing, something that we called topic modeling. So all through the training thus far we have looked at things like how do we structurally uh, represent text data in the form of a document term matrix. Then we have looked at some of the commonly used methods for representing text data as features. We looked at the bag of words model. We looked at the concept of term frequency, uh, and then also we discussed that what are the common disadvantages of using term frequency for representing word as features. And then we touched upon in detail the concept of term frequency, inverse document frequency, which is something we will use and is used more often than not when it comes to representing text data in the form of features. Now, and also we looked at some of the methods for doing some exploratory data analysis using text data. Things like looking word distributions, looking uh, positional analysis or context window analysis, so on and so forth. So all of that was word or text pre-processing or exploratory data analysis. Now this is where with this topic on topic modeling, we go into more meatier things and we go to the crux of the topic on NLP. Okay, so the topic is topic modeling, and we will be using an algorithm called Latent Dirichlet Allocation, abbreviated as LDA, for implementing topic modeling. It might sound like a tongue twister, the name of the algorithm, but I'm sure by the time we are done with this video, I'll be using this term often enough for you to get accustomed to it. So, what is topic modeling? So, if you start off with an introduction and a very simple and concocted scenario, maybe. So let's say you land up in a news website. These days, there are many websites, which gives news across different domains aggregated together. So let's say you land up in one such website, and then you see that there are news across different categories. There are sports news, then news on local affairs, international affairs, then political news, entertainment news, and whatnot. So what you do is you sample 50 sentences from some of the news stories from each of the categories. Okay, so you take 50 sentences randomly from news in the sports category and 50 sentences from the international news category, so on and so forth, and then you put them together in the form of a text data, and you kind of jumble them up. You jumble up the sentences. So once you have jumbled them up, you don't know that which sentence has originated from a sports news section or which sentence has originated from a politics news section. So you have no notion of that. So now, the question is, shall there be an algorithm, or rather, is there the need of an algorithm uh, which can help you organize the jumbled up text in the sense that from your jumbled up collection of text, the algorithm can do a kind of a grouping so that it can group the text into different groups, and each group will be and the groups will be mutually exclusive and exhaustive, and each group will be homogeneous with respect to the news domain, and across different groups there will be heterogeneity with respect to the news domain. So essentially the algorithm will try to clear up the mess that you have created by jumbling up the sentences from different news categories. If it gives you, let's say, 5 groups, then optimally you would want group 1 to have most of the sentences which are derived from sports news. Group 2 should have most of the sentences that is derived from news related to politics, so on and so forth. So This is the kind of a task which an algorithm like topic model will do in the context of natural language processing. So now that I have described in a very laymanish language that what kind of task or what kind of job a topic model algorithm will perform, does this sound similar to you? Is this a similar problem that you have solved or you have faced in some context or the other? And I'm sure this is indeed ringing a bell for most of you looking at this video, because this problem of topic modeling is kind of analogous to the problem of clustering that we have often done on numeric data. So if let's say if you have a numeric data on uh, age and income, and if you try and build clusters out of them using any unsupervised learning approach, you're typically you would want to have, let's say if you are aiming at 4 clusters, you would want to have one cluster where age is high, income is low, another cluster where age is low, income is high, and so on and so forth. So each cluster you would want them to be homogeneous as much as possible within themselves, and between the clusters you would expect as much of heterogeneity as possible. So it's the same idea which has been translated into the world of texts. So if you have a collection of texts which is kind of a mixed bag, topic modeling is an algorithm which will group your text into certain non-overlapping groups, so that each group is homogeneous with respect to one or two of the topics. Okay, so that's what topic modeling is intended to do. Now, why on earth do you want to do something like this with text data? So definitely, not just for the sake of doing it, but there are genuine use cases or business problems across different domains which can be solved using this kind of an algorithm. So think of it, I'll just cite a few examples. So if you are running a business, and let's say for your business you have a services business, and for your business you have a Facebook page, right? And your clients who follow your page, they go there, they write good things, and often they write bad things as well. I mean, if their experience is not good, and you as the owner of the business, you want to find out that what kind of posts are being posted in your business, in your Facebook page of in the Facebook page of your business. So some of the posts may pertain to specific services that your business offers. So you'd possibly want to go to the bottom of that to find out more insights. For example, just to give a more specific example, let's say if I look into TripAdvisor reviews, right? And if you are the owner of a hotel which is listed in TripAdvisor, and it has got uh, a good number of reviews being posted there, you will optimally want to look at those reviews, and also want to maybe group your reviews into certain groups, so that one of the group is, let's say, about uh, how easy it is to book your hotel or find out accommodation availability. How are people talking about the booking process? Another group maybe, where people are giving feedback about the overall quality of the room, and the space that is there in the rooms. And then there may be yet another group of reviews where people are talking about the food that is prepared in the in-house restaurant, the quality of that, the cost of that, so on and so forth. Uh, so the reviews taken together will be a mixed bag with respect to topics, because typically different customers will speak about different aspects of a hotel when they are writing a TripAdvisor review. So as a business owner, for you it will be extremely important to first of all segregate each of the categories which are being talked about, and then within each group try and analyze that what is uh, what is the core thing which is being talked about each of the categories. So that gives you more kind of directed insights rather than getting holistic insight about the overall reviews which is there. Similarly, let's say from a banking perspective, these days most banks have Facebook pages, right? So, and often customers go to the Facebook pages, and if they have a good experience to share, they do it, or if they have any grievance related to any product or any process, they write it there as well. So as a bank, you might be interested to analyze your Facebook page to find out that what are the distinct topics or the different topics on which the customers are posting there. Are they posting about something to do with account opening, or are they posting about something to do with calling your contact center or getting support on some of the banking process? So what are the topics? What are the things that they are talking about? So how do you really segregate them into homogeneous groups, and then look into each group? So that is what so the problem of topic model solves, and it's a very pertinent problem across many business domains, as I was just mentioning. So the assumption here is that, and it's a basic assumption on the premise of which the concept of topic model is actually developed, that if you think of your entire collection of text data, there are many hidden topics in it, and the objective of the algorithm is to find out those hidden topics, and then the topics are distinct from each other, and hence if you look at each topic, there are distinct set of words within each of the topics. So since the topics are very distinct from each other, the words which are present in each of the topics will also differ from each other. So these are the very basic underlying assumptions on which the concept of topic model is developed. Now, the approach that we will discuss for topic modeling, the algorithm which we will discuss here is perhaps one of the most popular algorithms for topic modeling, which is called latent Dirichlet allocation. But having said so, there are other algorithms available as well for extracting topics out of text data, but LDA or latent Dirichlet allocation is the most popular of the algorithms, and there is support of this algorithm both in R as well as in Python, so you can very easily implement this algorithm on your text data. By the way, just like we had for the other training videos as well, for this one as well, we will have a detailed hands-on session with R, wherein we will see that how we are implementing topic modeling using the algorithm latent Dirichlet allocation LDA. Okay, so but before that, let's get the theory out of the way. Okay, so latent Dirichlet allocation is basically a Bayesian probabilistic model. Now, don't worry about this term too much right now, because it's just for the sake of knowing that it's a Bayesian probabilistic model, and once we move on in explaining what the latent Dirichlet allocation algorithm does, uh, it will become clear that where the probabilistic part comes in and where the Bayesian part comes in. But this is, just for the sake of information, and knowing or not knowing this part will not be an obstacle for you to understand how the algorithm works at a high level. Okay, so as I was saying, LDA is based on two fundamental assumptions, and these are very intuitive. So these are not assumptions, which will make you think a lot, because it's kind of a no-brainer. It's very intuitive assumption. The assumptions are that documents are composed of hidden topics. So the text data that you are dealing with, it will consist of different hidden topics in it. The topics are not always visible, uh, but you can, if you analyze the text, you can figure out what the topics are. And then the topics are also composed of words, and just like the topics can be distinct from each other, the words which are present in each of the topics will also be distinct from each other, which is not to say that they will be completely non-overlapping. There will be words which will be present across multiple topics as well, because and that's the nature of language. I mean, there are some words which can be used in multiple contexts. So obviously you will not see, across different topics, the set of words are completely non-overlapping. That's not possible. But then there will be some words which will be present in some topics more often than not. Okay, so statistically speaking, what we can think of is, if we think of a probability distribution of topics over documents, then we can perhaps uh, enumerate all the documents, in the sense that, let's say, we assume, what does this statement mean? So this statement means that, let's say if I have 100 documents, which means I am dealing with a data of 100 observations, and I say that there are three distinct topics, hidden in these 100 observations, and I assume a probability distribution. Let's say these three topics, how they are distributed across the 100 documents. Let's say I say that 40% of the documents are pertaining to topic 1, and another 25% of the documents are pertaining to topic 2, and the remaining 35% of the documents are pertaining to topic 3. So all that I'm doing here is I'm basically saying that the distribution of topics above documents is 40, 25, 35. So I'm assuming a probability distribution of the topics over a documents, a very simple one. So that's that's one way of statistically formulating the problem as far as the topics and the documents are concerned. And then similarly, as I was saying previously as well, that uh, topics will have words within them, so you can also assume a probability distribution of all the words over a given topic. So you can make statements like, what is the probability that a given word will be present in a given topic? And obviously, as we are saying that the topics are distinct from each other, some words will be more likely, probabilistically more likely to be present in some topics than in some of the other topics. So that is how the probabilistic foundation of our topic model is conceptualized. But before we go into more theory, let us take a simple example. So let's say we have 5 documents or 5 observations out here, and these are basically 5 simple sentences, and these sentences are, if you read through these sentences, you will see that there are 2 hidden topics out here. And since there are just 5, they are just 5 in number, you can read and make it out. But in a real life scenario, when there are tons of documents, obviously you won't be able to read through all of them and find out the topics. That's where you need the algorithm. So if you read through the sentences here, the first sentence, it talks about some of the breakfast items, so peanut butter sandwich, and then it talks about what it talks about some nuts, almonds, peanuts, and walnuts. And then the third document, it talks about my neighbor has got a little dog yesterday, so it has got nothing to do with food or breakfast. Document 4, it again talks about pets, so pets are enemies, cats and dogs are enemies, so that's what it talks about. And then document 5, it's a combination of uh, food and pets both. So it said that you must not feed peanuts to your dog. So if you just read through these 5 documents, you will see that there are 2 topics very apparent out here. So one is related to food or breakfast or nut, whatever way you may call it, and the other one is related to animals or pets, right? And then these are the 2 topics, and document 1, 2 are exclusively about topic 1, which is breakfast or food or nuts, whatever you name it. And documents 3 and 4 are exclusively about pets or animals. There's nothing to do with food mentioned in documents 3 and 4. And document 5 is actually a combination of topic 1 and topic 2, because it talks about both food as well as about pets. So this job which you which you were able to do in an incredibly easy manner, just by reading through the 5 sentences, becomes massively difficult when there are loads of sentences, loads of text data, and not just 2 but many hidden topics in it. And that's the task which uh, latent Dirichlet allocation algorithm will help us do, topic modeling. Okay, and in this case, if you recall, when I was saying that topic 1 and topic there are 2 topics, one about food, breakfast or nuts, and the other one about animals. uh, what topic modeling will do is and we will look at it when we go through the rest of the video. It will give me the topics and it will give me the underlying words in each of the topics, but it will not explicitly tell me that this is how you label this topic or this is how you call this topic. So for example, in this case, the fact that I am saying that topic 1 is about breakfast, food or nut, that is my interpretation by looking at the words present in that topic. So even when I do a topic modeling, and it throws up the topics and the most prevalent words in those topics, so I have to go through the words and interpret the topic myself. The algorithm will not do the interpretation of the topic, so it will just do the segregation of the topics, and then for each topics it will give me the most prevalent words, and then basis this results I'll have to interpret the topics. Okay, so that's the simple example I wanted to give you right at the onset so that things appear less fuzzy. And I hope it's not appearing fuzzy now. So this is precisely the task we will now try to achieve, not on 5 sentences, but on a lot more than that, sentences, lot more than that. Okay. So where does the concept of probability distribution arises from in the context of topic modeling? So if you look at, if you think of the document term matrix, which is the way of representing text data. So what we said was in the document term matrix, it's the rows are the different documents, the different observations, and the columns are the different words, the number of distinct words which are present in the document. So then the order of the matrix is number of rows is equal to the number of observations, and the number of columns that you have is equal to the total number of distinct words, which is the size, which you also call as the size of the vocabulary. So in the document term matrix, if you look at any element in the document term matrix, it actually tells you that number of times a given word has appeared in a given document. So essentially, what the document term matrix can help you do is it can find out, it can help you derive the joint probability distribution of document and word, because in the document term matrix it's precisely this information which it is loaded with, right? So number of times different words are present in different documents, uh, you can think of it as a measure of the joint probability distribution of documents and words, right? And now probabilistically, the joint probability distribution of documents and words can be expressed in a format like this. So I'm not going into the derivation of this, that how the conditional probabilities are coming out in this expression, but then it turns out to be that that the joint probability distribution of documents and words can be expressed like this. And in this expression, if you look at probability of a document, that is something which is an unconditional probability, and it is independent of the words or the topics. By the way, W here refers to word, Z refers to topic, and D obviously refers to document. So probability of a document is independent of the word or the topic. So it's simply, if you have 100 documents, then probability of having one of them is 1 by 100, right? So it's independent of both the topic as the words. So that's why it is out of this summation, and we will not be bothered much about this. Neither is this quantity going to help us in defining the topics. So what we will be bothered about are these two conditional probabilities. So the conditional probabilities within the summation, so these are what that we will be bothered about, and for the right reason. So let's look at how do we interpret these conditional probabilities. So if you look at the first conditional probability, which is Z given D, where Z is the symbol for topic and D is the symbol for document. So probability of Z given D is the conditional probability that a topic Z is present in the document D. So in the context of that 5 sentence example I was discussing in the beginning, it can be interpreted as the probability that the topic on food or breakfast is present in document 1, or the probability that the topic pet or animal is present in document 1, so on and so forth. So it is the conditional probability that a particular topic is present in a given document. Okay, and the second conditional probability, it's actually called the first one is called the topic given document probability, and the second one is called the word given topic probability. So recall, what we were saying. We were saying that in topic model, the two basic tasks we have to do is we have to find out distinct hidden topics, and then within each topic we have to find out that what are the most prevalent words. Some words will be present in some topics more often and less often in some other topics. So obviously we need to look at the probability distribution of words given a particular topic, and obviously this distribution will vary from topic to topic, right? So these are the two components, two conditional probabilities, which are perfectly aligned with the purpose of, or the aim of, topic modeling. So aim of topic modeling is we find out that what are the hidden topics. So essentially we find out that for every document, which are the topics, or if it is a single topic, which topic this document actually pertains to. So that is something which is very much analogous to the first conditional probability, wherein we are looking at the conditional probability of different topics given a document. And then the second objective of topic model is also to find out that within each topics, what are the most prevalent words. And if you look at the second conditional probability, W given Z, word given topic, that actually gives us what is the likelihood that, or what is the probability that a particular word is present in a given topic. And obviously some words will be more likely to present in some topics than in some other topics. Okay, so that is where the that is how the probabilistic foundation of topic modeling is laid down, and it is perfectly aligned with the two fundamental assumptions of the topic model, that mm, text data is composed of some hidden topics, and then every topic have a distribution of words in it, and depending on the distribution, some words are more likely to present in some topics than in some other topics. So where does the Bayesian thing comes out to be here? Because if you recall, uh, in right at the beginning, when I introduced the term latent Dirichlet allocation, I was saying that it's a Bayesian probabilistic model. Now why we are calling it a probabilistic model is must be very apparent by now, because we have represented the two fundamental assumptions of topic modeling using two conditional probability distributions, where the Bayesian, and we'll quickly touch upon now that why we are calling it a Bayesian probabilistic model. Now if you before that, if you look at these two distributions, right, probability of topic given document and probability of word word given document, right? So these are what kind of probability distributions do you think they will be? Now for the first conditional distribution, if you think that there are key topics in totality, if we assume that there are k hidden topics in the data, then this will, the first conditional probability is actually a probability of one of the k topics uh, being present in a document, or in other words, or even in better words, it is basically the probability of each of the key topics. What is the probability that, with what probability each of the key topics appear in a given document? So clearly it is a k class multinomial distribution, right, which is a generalization of the binomial distribution. And then if we look at the second conditional probability, which is W given Z, or word given topic, it's also, and in this case if we assume that W is the set of all distinct words, and then and the size of the vocabulary is actually W, so we have W many distinct words in the data, then this is also a multinomial distribution over W classes, right? And little bit of a concept from Bayesian inference theory out here, that for multinomial distributions, when we assume a prior distribution for the multinomial class probabilities, the prior distribution is taken to be Dirichlet distribution, and the reason is, Dirichlet distribution actually gives a conjugate prior for multinomial distribution. So I'm not going into the details of that, not just for the sake of complexity out here, but also because it's not necessary to understand this part to the fullest detail to be able to understand the topic modeling concept. But those of you, who have some context into Bayesian inference, I'm sure would appreciate that why we are assuming a Dirichlet distribution for the prior distribution of the multinomial class probabilities. But nonetheless, if you do not have a context into Bayesian inference, there's nothing to worry about. If you don't understand this part, this is not going to stop you from understanding anything that I'm going to talk about in the rest of the video. Okay, so that's where the Bayesian part comes in, and that's where the Dirichlet distribution is getting used, and that's why it finds its place in the name also, latent Dirichlet allocation. Quite a fancy name. Okay, so moving on. So what we see here is that these two conditional probabilities, these are starting out to be things of paramount importance, right? Because these conditional probabilities are actually analogous to the two fundamental aims of topic modeling, right? Finding out what are the hidden topics in the data, and also finding out within each topic what are the most prevalent words. So it boils down to that if we can somehow, you know, obtain these two, obtain some estimates of these two conditional probabilities, then possibly the problem of topic modeling is solved, because these two are analogous and completely aligned to the objective of topic modeling. Now, we have been focusing on the right hand side of the equation all through, mostly. For a moment and for a change, let's look at the left hand side. Now the left hand side is basically the joint distribution, the joint probability distribution of documents and words, and this is something, as I was, I think as I was briefly mentioning at the beginning, that this is something which can be estimated from the document term matrix. So which means that the left hand side of this equation is analogous to the document term matrix, right? And and the right hand side has two components, two set of conditional probabilities which are of paramount importance to us, right? So logically speaking, intuitively speaking, if we can somehow decompose the document term matrix into a product of two matrices, then we should be able to make some headway, right? And I made a very important statement in a very casual note, but it's basically a very important concept when it comes to uh, understanding topic modeling. So I'll reiterate again. So if you look at the left hand side of this equation, it has the joint probability distribution of the documents and words, and this is something which can be estimated from the document term matrix. Whereas on the right hand side we have the product of these two conditional probabilities which are of paramount importance to us as far as the objective of topic modeling is concerned. So if we can somehow decompose the right hand side, and the right hand side we can estimate by the document term, sorry, if we can decompose somehow the left hand side, which we can estimate from the document term matrix, if we can somehow decompose the document term matrix into two matrices, then I think we have a way to move ahead. Let's see what's the way. So there are again, I'll state this without going into the proof here, because again, the proof is complex and it's not necessary to know the proof to be able to understand how topic modeling works. So matrix D can be factorized into two of the product matrices M1 and M2. So there are matrix factorization techniques using which it can be done, and D in this case is the is the DTM, or the document term matrix. And as you would all know, the order of D would be n cross W, where n is the number of documents that you are dealing with, and W is your size of the vocabulary, or the number of distinct words, unique words which are present in your data. So if you can decompose the document term matrix into two sub matrices, product of two matrices which are M1 and M2, that's what we are naming them here, such that M1 is of order n cross k and M2 is of order k cross W, so that the matrix multiplication is conformable, and k is not just any arbitrary k, but k is basically the number of topics that you are assuming which is present in the data, or the number of topics which you want to find out from your collection of data. So that is what k is, right? So then M1 is called the document topic matrix, because if you see and if you also see the dimension of M1, you know there are as many rows as are the number of documents, and as many columns as are the number of topics that you are interested in the given data. So M1 can be conveniently termed as the document topic matrix. Similarly, M2, if you look at the number of rows for M2, it has k rows, which is basically the number of topics you are aiming to have, and the number of columns in M2 is basically equal to the size of your vocabulary, which is the number of unique words. So again, M2 can be conveniently interpreted as the topic word matrix, right? So quickly reiterating, so we can decompose the document term matrix into two matrix products, and the matrix products will have dimensions such that the multiplication is possible, and it turns out to be that the matrices M1 and M2, their dimensions are such that they can easily be used to make inferences or make estimations about the document topic probabilities, which is the conditional probability of topic given document, and from M2 we can get the topic word probabilities, which is basically the probability of word given topic. So this is a major step forward, because if we are able to do this matrix factorization, as we will see later on, we can actually estimate these conditional probabilities, which are uh, very important components as far as topic modeling is concerned, because these conditional probabilities will eventually lead us to what we aim to achieve from topic modeling. Now, these matrices M1 and M2, uh, they give us the distributions of the uh, topic given document as well as the word given topic. But then these distributions need to be improved, because and we'll quickly see why these distributions need to be improved from their present state of things. So how does the matrices M1 and M2 get improved? So think of it from a estimation problem perspective. So what you're trying to estimate here are two conditional probability distributions, right? And again, one of the common approaches for estimating distributions is doing resampling using techniques like Gibbs sampling. So the same concept is used out here. Again, if you do not have context into Gibbs sampling, don't worry, it won't stop you from understanding how the algorithm works at a high level. But if you have the context into Gibbs sampling and estimating distributions, I'm sure you can you can very easily relate to what I am saying out here. But if you are not able to relate, don't worry. You'll see that it's not going to be a showstopper for you. So how the algorithm gets initiated is, it first runs through every document, one document at a time, right? Or one observation at a time. And then as it goes from one observation at a time, for a given document or for a given observation, it randomly assigns each word in the document to one of the key topics, which is your aim, right? You have chosen K beforehand in terms of a number of topics that you want to find from your data. So, so let's say if there are 5 topics, if k equal to 5, then for the first document, what the algorithm will do is it will randomly assign each of the word in the first document to one of the 5 topics. In assuming that there are 5 topics you are aiming to arrive at, and this is how the using this random allocation the matrix factorization happens. But then the random allocation is not good enough, right? Because we don't want a scenario where we say that all words are equally likely to present in all topics, because that serves no purpose. We want a scenario, we want a structure where the topic should be such that some words are more likely to present in some topics, and similarly they are less likely to present in some of the other topics. That is if that is the scenario, then only we will be able to interpret the topics. The first the matrix factorization, the way it happens, it basically randomly allocates every word to one of the k topics which you are trying to arrive at. So how is this random allocation further improved upon? So there is where we use the concept of Gibbs sampling. So, so what happens is, once the random allocation has been done for all the documents, then again the algorithm reinitiates from the first document, and it tries to reassign a word to a new topic. Because previously when the matrix factorization was done, the words were randomly allocated to topics. So now it tries to reassign the words to a new topic, and the reassignment happens with a probability which is the product of these two conditional probabilities. So the topic given document and the word given topic, but just that this topic is not the one to which the word was initially randomly assigned. So this is a new topic, right? And this step is performed iteratively again and again over the full set of documents till the time a steady state is reached. And in this case, a steady state is something which would be, that we have reached a state where we have identified the desired number of topics, and then and we have word representations in each of the topics such that some words are more likely to be present in some topics, some words are less, and consequently they are less likely to be present in some of the other topics. But having said so, a word of caution, it's not guaranteed that given any data and given any choice of k, which is the number of topics you want to arrive at, you will always get that kind of representation. So that is where so for example, if you have a data which is very homogeneous in itself, so it talks about only one particular topic, and then you are demanding the algorithm to generate 10 distinct topics out of that data, it will definitely not work, right? Because it's very homogeneous with respect to the topic. There's only one topic, and hence a common set of words keep appearing time and again. So choice of k is key. So it's iterative. You can try out with different choices of k and see that what choice of k is actually giving you the desired structure. And the desired structure here is where within the topics, when you look at the words, some words are present more often than not in some topics, and they are present with lower probabilities in some of the other topics. So that is how the algorithm works. Now, time for some board work. So it's not the simplest of the algorithms, topic modeling. Let me admit that, but not to scare you off as well. So what I will do here is I'll do a very quick and uncomplicated recap of what are the different steps involved in doing topic modeling using latent Dirichlet allocation. So step one is basically saying that, but obviously step zero is a step zero to it. The step zero is the basic underlying assumption of a topic model, that the data that you have has several hidden topics in it, and you start off with an assumption that how many topics you want to find out from the data. And then the second assumption is that each topic, every topic might have every word present in it, but then some words are more likely to be present in some topics than in some of the other topics. So maybe that's a step zero, which is not featuring here, but that because that's an assumption. But as far as the execution of the algorithm is concerned, step one would be, you represent the document word joint probability distribution using this expression, and the left hand side of the equation here, which is the joint probability distribution of document and word, is something which is very much analogous to the document term matrix, and the right hand side, the probability of the document, is something which is independent of the topic and the words, so that's out of the summation. And these two conditional probabilities, the topic given document conditional probability and the word given topic conditional probability, are the two terms of supreme importance out here, because these are the two terms which if we can estimate, they will give us what we aim to achieve using topic modeling. So step 2 is essentially to estimate these two conditional probabilities, and the subparts in step 2 are: we assume a multinomial distribution for both z given d and w given z, because z given d is basically the conditional distribution of topics given document, and there are, if we start off with an assumption of k topics, so it's a distribution of over k topics, which is something where multinomial exactly fits into, and similarly for w given z as well. And we assume a Bayesian approach here. So for multinomial distribution, Dirichlet prior is the right choice of prior, so we assume Dirichlet prior. Once again, if you're not familiar with Bayesian inference, you can skip 2b, point number 2b. That's not going to stop you from understanding this algorithm at a high level. And the third step in step 2 is basically factorize the document term matrix into two sub matrices, two matrix products, which will give initial estimates of these two conditional probabilities. And how the initial estimates are obtained is at the initiation stage, in every document, every word is randomly allocated to one of the k topics. And then this allocation is further being improved upon by using Gibbs sampling. So, and by improvement, we mean that we want to reach a steady state where uh, the topics have been identified in such a way that some of the words are present in some of the topics with higher probabilities, and consequently they are present with comparatively lower probabilities in some of the other topics. Okay, so that is how this algorithm works in a nutshell, and we will do the hands-on of LDA using R, where you'll get a closer look into how things work. You'll get a better hang of it. But before that, for the sake of completeness, and just to ensure that you uh, you end this video with a note that this algorithm indeed works, let us look at how does an output of a topic model look like typically when you run the algorithm in R. Obviously, when we do the hands-on, we will look at a more real form of this output, but the final output luckily is much simpler than, much less complicated than what the algorithm is. So it gives as an output two matrices to you, as simple as that. And you would have already guessed what these two matrices are. So they are the two the matrices which give the conditional probabilities of topic given document, and the conditional probability of the topic given word. So the matrix M1, which is the topic document matrix, So it is a n cross k matrix, where n being the number of documents and k being the number of topics you aim to arrive at. And the ijth element of this matrix is basically interpreted as what is the probability that the jth topic is present in the ith document. So it can be something very close to 1, or it can be something very close to 0, depending on whether or not document I pertains to topic J or not. And by the way, as we saw in the initial example we started off with on food items and pets, some of the documents can have mixed topics as well. So you can have, so some of these probabilities can be, they need not always be close to 0 or close to 1, so they can be something in between as well, because some of the documents can have a mixture of multiple topics as well, right? So essentially this matrix, and since the very nature of the matrix is such that it gives the conditional probability of the topic given every document, the rows add up to 1, because these are probabilities of different topics across a given document. So the rows add up to 1, and within every row the topics which are present with significantly higher probabilities are the ones to which these documents would relate to. So that is about the topic document matrix. And then M2, the other matrix which we get as an output, is called the topic word matrix. So it's basically the conditional probability of words given topic. So again here the number of rows are equal to the number of topics that we are trying to arrive at, which is k in this case, and the number of words, number of columns are equivalent to the size of the vocabulary, which is a number of distinct words in the data w. So the order is k cross w, and once again, the ijth element of this matrix is interpreted as what is the probability that the jth word appears in the ith topic. And once again, it is these probabilities which help us understand that which words are more likely to be present in which topic, and which words are less likely to be present in which topic. And it's essentially the words which are more likely to be present in certain topics which help us interpret what is the context of the topic, right? So, and also just similar to the matrix M1, in M2 also the rows will add up to 1, because if you look at the first row will be interpreted as probability of word 1 in topic 1, then probability of word 2 in topic 1, so on and so forth, and all these probabilities will add up to 1. So similarly all the rows of the matrix M2 will add up to 1. So these are the two outputs that we get from when we run the topic model in R. When we do the hands-on, we will have a closer look at it, and we will try and interpret some of the topics as well by looking at the probabilities of different words, which words feature with higher probabilities in the topic. So that was all about topic modeling. Hope you enjoyed this video, and stay tuned for more. In the next video we will do hands-on on topic modeling, and hopefully that will give you a closer look at how this entire thing works. Thank you for watching. Stay tuned.